Hello and welcome back for our next emerging science of anaerobic digestion. I'm super excited to have Lauren Ray presenting today. I got to see her at Waste to Worth last year, talking about some of the work she's been doing on observing leaks from digesters, and thought, man, that is a great topic and one, unfortunately, we know so little about. And she brought a lot of great science behind it, had some great pictures and visuals of what leaks look like. So super excited to have her joining us today and talking through the work she's been done. And yeah, look forward to the message. And at the end, we'll have some chances for questions. So if you want to learn more about some of the detection methods, I'm sure she'll share some of her techniques with all of us. So with that, thanks, Lauren, for joining us, and excited to hear what you have to say.
Yeah, thank you, Dan. Hi, everyone. I'm Lauren Ray. I am with Cornell University and specifically with our Pro Dairy program, which I have a little overview here, provides extension education and applied research programming to support the dairy sector, specifically dairy farms in New York State. So this has been in place, this program has been in place for over 35 years now. I think we're not quite at 40. And you can see we have about 15, or it kind of ebbs and flows, but specialists, and apologies if I don't have this fully updated, but I think it's pretty close. So we, are a team of kind of specialists in different areas. You can see up there, I'm in the dairy environmental systems, or really in the, now we're kind of having a term of energy systems too. There's a lot more energy systems work that we see on the forefront with utility rates increasing in New York's climate law, kind of transitioning us a lot in the energy space. So, but yeah, we're under environmental systems. And so I just kind of put that in context for you. We work hand in hand with like broader extension agents in the state as well to get the messaging out. So what we're going to talk about today is the work that specifically the Dairy Environmental Systems Group has done in the last, I guess it's been 2.5 or so years, actually even dates back before that to kind of prep for this project. But we were able to do some methane loss detection work at commercial dairy farms in New York State. And then we did this on their biogas capture systems. So as Dan said, that did include anaerobic digestion systems. It also included covered and flared manure storage systems. So we do have farms, several now that have the cover and flare on their manure storage. And I'm going to show you some images so you see the way these are set up in New York State, or kind of in the Northeast, the cooler climate, I would say, because it can be different than in other regions of the US. So just keep that in mind. So specifically, the project that we embarked on here with the commercial dairy farms that chose to participate with us was really to use a tool that we had investigated under a NYSERDA project, NYSERDA's Energy Research and Development Authority in New York State. We had really investigated what tools are able to be used to detect leaks from anaerobic digester systems was kind of the focus. It can be very hard to know if you have a leak or a loss. And what we found was really what the oil and gas industry is using, which is an optical gas imaging camera to find leaks in natural gas systems, right? Or otherwise, that tool actually worked obviously quite well on farm. And what was good about what we learned in that pre-work was that the lower grade or lower cost model of the optical gas imaging camera from Teledyne FLIR is the manufacturer we used. That was actually really acceptable or able to find even small leaks and losses in our system, whereas the more expensive model we found we didn't need. So I think that was good to determine. One of the reasons for that is because we're able to be on site right near the system, whereas sometimes for oil and gas, they're scanning from kind of far away or they just don't get real close. So really proximity, distance matters with this tool. So I think I have some more slides that'll sort of get in that science of the how this camera works. And so we'll talk about that soon. But just know it's the GF77 model, which is an uncooled um, optical gas imaging camera. And we assessed over the course of 1 year for each system, um, and 4 different visits for over that year. So kind of each quarter was the goal. We assessed a total of 6 anaerobic digester systems that went to energy systems, different ones. We had electricity generation for 4 of those, and then we had renewable natural gas generation with pipeline injection on site for 2 other ones. So we have had quite a few anaerobic digester systems in New York, some existing, some new that are now doing the renewable natural gas production rather than electricity. So that was kind of a transition we saw. Um, and let's see, I guess we did have different digester types. So we did have at least one plug flow anaerobic digester system. I might have a picture of that, or not like the exact one, but just what those are. I think most people can know what that is based on other presentations I'm sure that have been done. And then I'd say most of them were the complete mix type, like tanks. And then one did include renewable natural gas truck unloading at the location that we were serving because they had another farm that was bringing gas from their system over to the injection point. So just had some truck unloading as well. And then covered and flared manure storage systems. We had 6 of those as well. And most of them were just separated liquid manure, so no digesters involved. One of them did have a digester, so they actually had a cover and flare on the effluent of the digester, so digestate rate. And so we did assess that type of system, and different ages were done. So I wanted to just, yeah, here's a plug flow, at least the types that we've had right in New York State that you see by the aerial image there. So it's rectangular and in ground mostly, several feet, right? And so that was one of the systems, or at least we had one of those types. Also, the complete mix, what I'm showing down below is one of the smallest systems in New York State that we have operating on a farm. And that one does do food waste and so food waste and manure digestion. And really, we've had, I think that's actually showing the growth prior to where we are today. So I apologize that I don't think I included where we are today, but we've had growth where the number of cows that were having manure digested in 2016 there was almost, I guess it was around 55,000 cows. Where now the state is over 100,000 cows. Manure is going into digesters. So we've had significant growth. Um, and I would say New York does have 600 and I believe now 640,000 milk cows. So we've been right around that 630,000 total cows, just to give you an idea. So we're at a pretty high percentage of these systems in place when it comes to the animals that are going through there. So this is what also, just some more images of what types of digester systems we use here. So they definitely are tanks and insulated and heated. Okay, so just trying to put that in context compared to other locations where it's not cold. And these were the types of systems analyzed, right? This is what they looked like. So we had a big variety, some older, some newer, with the assessment that we did for leaks and losses. And then I want to just show you images of the cover and flare system so we get familiar with that and what we were able to look at. So these are the manure, you know, dairy manure storage systems that are used in our region and really Northeast, Upper Midwest. So, they tend to be not very large, right? Tend to be more deep. You see, obviously, we have different sizes, but this is where manure may be We often have scraped manure from the barns. I mean, that's much more common than any flushing systems. So what happens is if a farm has no manure treatments or any systems processing the manure, that'll be scraped and pumped right into a storage so that they can manage it on the landscape under their CAFO permit usually. So what I'm just showing you what this looks like. So obviously we have very cold weather at times, and these don't quite freeze or anything, but just have layers of snow and things. And what the cover and flare systems do is they put a cover over this storage in ground, right? But they don't have any heating or anything else. So it's a very passive system, right? And especially in our region when we have such variable temperatures. So it behaves very differently year round than, say, maybe Central Valley, California. So just keep that in mind as well. I think that makes it very challenging to look for leaks and losses from a cover and flare manure storage in these climates. So with the cover and flare systems, it's best practice to separate solids. Really, all the farms now that put these in or have them in are separating out manure fibers with typically a screw press, but there's some different systems first before the liquid side, liquid goes into the covered storage because, of course, we can't get out solids easily when it's got that cover on top. And then, real quick, with scraped manure from the barn, which is what we typically have as a practice rate in New York, with the screw presses, we tend to see farms getting about 40% solid or yeah, total solids in the separated solids, and the volatile solids is 40 to 50% is removed from the liquid side. But of course, we know that really that's all the larger fibers typically. So as far as like gas production goes, it becomes tricky, or that you have to consider the degradability of both the separated liquid and the separated solids. So degradability tends to be higher with those finer particles. Obviously, we can have, you know, those are easier for the microbe community to convert to methane biogas in the storage. So I guess just putting that, I know there are systems that separate solids that are more separating on the flushed dairy manure types of, barns and systems, and they can have very different separation efficiencies and results from that. So just wanted to show you what we're dealing with here. So the cover over the storage is high density polyethylene, typically HDP material. It's an impermeable cover, so gas tight and watertight. And this is what it ends up looking like. So it really does like float on top of the manure for the most part. And what happens is the biogas makes its way, again, passively, to the collection pipe that's around the perimeter. So you can kind of see in this picture, I don't know if you can see my mouse, but on the picture on the right, there's like a kind of a stitching with the cover. I mean, actually, I'm sorry, it's further in where that pipe's coming out. You see there's like a perimeter pipe. You can kind of see it underneath because that's where this main collection pipe that you see in each picture is or distribution pipe, I guess, is where all that biogas around the perimeter is ultimately funneled or, finds its way there, and then it goes into the flare. And you can see a flare, one type, in the background of the one picture. So that's a candlestick type flare. So this is very common, what we've seen put in so far in New York. There are some different systems out there now, and things are a little, shifting around as people learn more. We do have some farms that have an enclosed flare, like on the right there, instead of a candlestick. So, that's also an option. I know they can be more expensive, but I believe there's some advantages with things like, protection from wind and other things to consider with the actual combustion efficiency. So for these cover and flare systems, obviously the goal is burn the biogas so that we destroy the methane. So that's what's supposed to happen, right? And we want to understand both leaks and losses from the cover and then any in the system, the biogas system as well. So I guess I had a few notes over here. Basically, these flares, again, there is at least one or two systems now that are newer in New York that I think have more sophisticated monitoring and some other things as they are trying to kind of better set up these systems to capture carbon credits or otherwise. So, but generally they have auto ignition in place, and then of course safety with a flame arrestor and some pressure relief valves are on the cover itself usually. Um, and then they're monitoring the thermal flow to the flare, so whatever's collected in the pipe mass flow, thermal mass flow, and then the combustion status. So at a minimum, we're monitoring, those things are monitored and logged. Um, so just the temperature of the flare to confirm whether it's burning or not, right? Those are kind of the minimum requirements to really know what's going on with these systems. Um, so yeah, as I said, the optical gas imaging camera was the primary tool that was used to find and then record and describe bio losses that were present at the different systems at the time of the site visit. That when we were on site for about an hour, or sometimes a couple hours. So really, what the camera allows you to do is find point source methane losses, and it's able to do that because it has an infrared spectrum. Sorry, it has a lens that's tuned to the infrared wavelength where methane absorbs. So I think that was on my next. Oh, see, that must be the one that didn't copy, Dan. But anyway, if you look up where methane as a gas is absorbed on the infrared spectrum, you'll find that it is both at a shorter wavelength of like 3.5 micrometers, as well as at a longer wavelength, which is 7.5 to 8 micrometers. So what that means is the way these cameras are designed is the lens is tuned to one of those. It can't be tuned to both, and so that it can pick up the image of methane where the naked eye cannot. So I don't know if I described that well. So the more expensive model is the cooled camera. And that is operating with the lens at the short wavelength, so the 3.5 or so micrometers. Again, so what that model allows is for very sensitive detection of methane so that you can be further away. So it ultimately comes down to like the concentration of the methane is important as far as what you can see easily, but also the distance that you are away from that particular concentration source. So we use the long wave camera lens and model, and that is uncooled. So it's actually a lot less maintenance and things and not as much requirements for having it, I'm losing my word now, but you know what I'm like calibrated and things. You have to send the other one in occasionally to be calibrated. So this one's much easier to deal with. And it worked great as far as seeing what you needed to see. Even very small leaks were able to be visualized with this camera, as long as you could be within sort of, 100 feet or 50 feet, depending on the size. So one of the ways we conducted this work or really was to set up a protocol that we kind of improved on as we went along, methane loss detection protocol, and we had a different one for the anaerobic digester to energy systems versus the cover and flare systems. And just to give you a quick idea, um, we had kind of these different parts of the system to inspect, and then I'll walk through like what you can even record down when you have the camera, because unfortunately we can't measure the methane with the camera. And there's been a lot of discussion on that point, like, oh, what about the pixels? Isn't there a way to analyze it? And I think the Teledyne FLIR company at one point had a software that I think went along with the cooled camera, so the more expensive model, that they said could um, quantify methane using the pixels and some obviously software that was developed. What I found when I spoke with them about that is that it requires a very good understanding of exactly what environment this methane is in. You need to know the ambient temperature, I believe, like the wind as well, or a lot of the basically ambient environment conditions, as well as the biogas itself having a more steady flow or something like that. Whereas we're kind of dealing with mostly not knowing most of those things or having them change frequently with these systems. So it didn't seem like that software would really be useful right now. And I would hope that there's going to be work on that, because obviously everyone wants to know, well, how much methane are we seeing on the camera? But we can't answer that. So all we can do is describe it. And so hopefully you've looked at some of these titles at the top here, but basically we would record for each component or major part of the system whether or not we detected a leak or a loss. So it could be a vent rather than just a leak. Or sorry, rather than a leak. I guess being a vent is a known event, a known thing about the system. Obviously, that's happening usually because of safety or something not kind of operating normally, fully. And the operator of the system, whether it's the farmer or a third party, right, that's running that system, knows that that's happening. So it's like that's how a vent is described versus a leak being unknown until we find it. It may be known, right? And it may be something they know, but it's clearly a leak because it's a tear in the cover. It's something that's not normal or not intended for the way the system's designed. Um, so we would record whether or not, yes or no, and then the location. So you might have, for example, actually digesters aren't a good example, because really the digester covers were amazing. I believe with digester covers, if you have a leak in your cover, you're going to know. There was maybe one case where they had like a loss near a rivet or something. It was extremely small. And that was, generally we saw many leaks in really from tearing of those plastic covers on the digestate, or sorry, on the manure storage systems, right? Those were much more prone to having a leak right in the cover, and it was usually a tear, a hole, or something going on. So we would record potentially multiple. So we would kind of have each location so that we could log each individual leak or event. And then the characteristics of it. So that would mainly be whether it's continuous or like intermittent. So you might actually see sometimes more of like a cloud, or like more of I don't know, not a continuous stream basically, and you can record that. Um, and then the relative size is the other one, which I think as you use the tool, you kind of get better and better at assessing that. I mean, one thing is you don't want to, you have to consider where you are in respect to the leak, right? To kind of know the size. So if you kind of keep that as consistent as you can, then it's pretty easy to say that's a big leak, that's a small leak, or, compared to each other, certainly. Um, the other thing was the camera mode. actually has a normal mode, and then it has a high sensitivity mode where it kind of strips out a lot of the background information and things. I mean, ultimately, it's like a thermal image camera, sort of. It has that built in. So the high sensitivity mode is really nice to see like tiny leaks clearly. And so where you suspect by maybe you caught your eye or whatever it is, or maybe not, but you just always want to look in high sensitivity to see if you actually do see anything. And that was a way that we distinguished small versus larger leaks, was that like whether we could see it in the normal mode um, versus only seeing it in that high sensitivity mode. So I guess that was a lot of information, but just wanting to help you understand how we did this. And I guess I'll show a couple videos. So the other thing with the camera is that, and that maybe this is a product of the actual leaks and vents and whatever that we saw, but it's very hard to do a screenshot or like a actual picture on the camera to capture easily to the eye what that leak looks like. So the easiest way to see it is a video. So you end up kind of recording videos, at least to go back and analyze on the big screen, because like you're only looking at a little screen when you're out there in the field. And I think video is just an easier way to see a loss rather than like a snip image and things. So hopefully you can see this video running. Um, I'm switching, that was normal mode. So then I went to high sensitivity mode, and I know it looks horrible like those old TVs or whatever, right? But you see how much more easily you can see that clouding of biogas coming out. This is a digester, and it is an unused, well, it is a used port. It was originally designed to be, I think, where the pressure relief valve is, but that has been relocated or it's not there. It wasn't used for that. And so the farmer actually was using it to dose in some, I think, soda ash to keep, or at times to keep the system from foaming. So when he had foaming issues, he would use that. And so obviously with the clamps and whatever he kind of did there, it was not very well sealed. So it was a loss. And it was actually, I would call that more significant looking, larger than some of the other leaks and things we saw at times. And so it was something to address. Um, Actually, this particular case, since it's like a pipe, we were able to enclose it with like bags to measure, to try to measure and estimate the rate of loss and get an idea of how much methane that is, right? So I'll play it again. So when we did that analysis, which is not perfect, obviously, but we came up with that this loss that you're looking at here, if it's happening continuously year round, it would equal 2% of what's produced by that digester. So that's kind of a lot of times that's actually an assumption used in like carbon accounting is 2% loss or 3% from a digester. Um, right? And so that's interesting. But again, this is if it's happening year round. And this was not because I mean, he kind of knew it was happening. He said it used to be sealed better and it wore out. He did repair it and it was not seen again after that for at least 3 or 4 more visits that we were there. So, obviously this didn't happen year round, but just to put that into perspective. Um, and then this is a cover and flare system. And so here it's interesting. The flare is back here and it's running. It's operating. And then I think you can see this, but there's a pressure relief pipe, and it's actually quite large on this system. It was venting very significantly this day. And this is not always the case. It was actually, it was interesting here because you could see heat or, you could see, yeah, like that wave of heat above that pipe. indicating you're losing gas or but you couldn't actually see what we see on this camera. Um, right. And so the farmer was like, I think something's, I think the seal's off or something's not working quite right with it. And indeed, that was right. So he knew, but I think until he saw this view, he like wasn't really that concerned. And then he's like, oh, well, this looks horrible. Like, I think it's almost visually, gets you to move and fix your seal. So he did, and he was able to repair it. Again, one of the things with the cover and flare systems in our region is people have not been able to get carbon credits successfully from these. So I don't think there's much incentive to not have these working as well as maybe they could. And it's also a challenge because of how the gas production is changing year round with these, because we have such cold time periods and then we have our warm summer. So the bulk of the gas is in the summer, and the system has to handle all of that, but actually it can't do that real well. So it just becomes a bit challenging to manage, I think. Or at least there's been issues like this. So there are ways, so that I guess this is where I mentioned the leak versus event, and I think we're all good on that as far as how we determined, uh, sorry, logged and recorded what we saw. So we did differentiate leaks and vents. We thought that was important, you know, um, and and I mentioned these things like size, normal mode, high sensitivity mode, and continuous intermittent. We did know if the system was having an issue. We tried really not to go on those days, but I know there were a few things happening when we were there, for some of these. So mostly that was not an issue, though, like system not running correctly, I would say. Um, yeah. Oh, and then this is just showing, this is an older cover, so I should note that we did include some of these results, but we did look at brand new covers as well. So I just want to be clear that we looked at a variety. But this particular one obviously had a repair to some sort of tear before with this black stuff on it, but it had a crack in there that was about the size of a pen. I think it was a little less than that, but just to kind of show you comparing. And then there actually was an issue with one of the cover and flare systems that was brand new, where uh, it appeared that they had like a large, sorry, like a sudden increase in the flow of biogas, like the biogas that was generated under the cover was rising quickly, and it caused an issue with the flare where it actually seemed to kind of, I don't know if it backfired a bit, or I shouldn't say backfire, but it basically caused some like combustion coming from the flare that was really excessive to what it's designed for. So the flow rates were high, and it burst this connection point here, and there was loss of biogas where this cover meets the pipe here. So, just things that happen and have to be fixed again. Um, so I'll finally get to what we observed, and really I would call these preliminary results right now as we're continuing to analyze things and get everything ready for a publication on this. But actually, I'll start with the one. So really, with the 12 different systems we analyzed, um, and I did break them up with digester systems versus cover and flare, so 6 of each. This is showing you the total count of methane losses. So it would be leaks or vents, and I guess I'm showing leaks and vents with the blue versus the orange. So blue is leaks and orange is vents. And this is the total count of unique, which means it was a single location, a single, leak or loss or vent. And it might have been repeated, but it was sort of its own. We just wanted to obviously determine whether or not it was a repeated leak on this on a subsequent visit. So we kind of said unique leaks here. So it's really like one-off, not including if there were repeated leaks. I don't know if that made sense, but we see mainly that the digester systems had, well, it had less overall counts of unique losses than the cover and flare systems did. You can see we had about like 21 versus like 47. But you see how with the cover and flare systems, um, we actually had predominantly the leaks occurring, not vents. And I'm also showing a repair rate, but I have that on the bottom screen too. So we'll look at that or when I advance. But there was pretty good repair rates here. We had 44% of the leaks repaired by the next visit, I guess is the way to look at that. And then 56% repaired for the cover systems. And there was a fair amount of repetition when there was a vent at a digester where it was observed again. So that, can indicate things are not maybe running as designed, or maybe things have changed right from the original place in service where they have too much gas, maybe. I mean, we did have electricity systems, so some of them were, maybe not able to, sorry, their engine or was at capacity and they still had excess biogas. So really the only option is vent or flare. And obviously we want to flare, but maybe the flare wasn't functioning. And that's why they had vents. So this chart is showing you more the breakdown of size between the two different types of systems, and then really obviously including the full count of losses. And in this case, the count is including repeated losses. So the first chart is showing just the unique ones, not any repeats. And the second one is showing you the total, including repeats. So the numbers on the bottom are different. So the normal mode is again what I would call a larger leak, and this high sensitivity is smaller. So really, we actually saw, I don't know, both on these systems. We actually saw a pretty high percentage of what I would call larger leaks and losses for the cover and flare systems. And the digester systems were at 40%. Sorry, the people are blocking my view of this. So, yeah, cover and flares were at 63. So just quick on the repeated methane losses. So obviously the first visit, we can't record any repeats, right? But then the second visit, we would record a repeated loss that was seen from the first, and also any new ones, and then we'd kind of carry that forward. So what we found with cover and flare systems is that all of the repeated losses were leaks, not vents. I think we kind of see they don't have a lot of vents anyway. The digester systems, though, were the opposite. Really, 16% of the repeated losses were leaks, so only 16%, and then 84 of the total repeated losses were vents. So again, if a system is venting, like a digester, it tends to be an ongoing issue that maybe needs a bigger change. Obviously, it's not a quick fix or just a repair. It's maybe a system function issue and needs to be almost like a redesign or something to address that. So I guess I'll leave it at that, and hopefully we do have some time, I think we do, for questions. And just thanking funders and supporters that we had really primarily for this project and all of the site work. It was Agriculture and Markets and New York State's Department of Ag and Markets. And then I mentioned NYSERDA before because we did have funding that really kickstarted all of the investigation into the tools that could be used for methane detection and the protocol to develop to actually do this. So I think, yeah, take it
Perfect.
away.
Yeah, thank you so much, Lauren. And we did get a few questions for you. The first one that I wanted to address is they just had a question about who was actually solid liquid separating. And I think you said all the covered storages, but not the ADs. Could you just provide some clarification there?
Sure. So, right, with the cover and flare manure storages, those are the farms that have solid liquid separation before that storage, and so it's the separated liquid that's going under the cover. And that's pretty universal now. I will say some very old systems didn't have that, but now those are not really operating anymore for the most part. So it's best practice to separate, and everyone's doing that. And they're typically using that screw press. And then digester systems, it's mostly common to separate after the digester. So the scraped manure from the barns goes right into the digester, and then the effluent digestate is separated often, but not all the time, to get fibers for bedding. So that's the most common practice.
Perfect. And then I think our most recent question here is really interesting. So, how was digestate typically stored after it came out of the digester? And did you look at any emissions of the digestate?
Yes, yeah, good question. So predominantly the digestate is stored in just as raw manure, right, is at least on our farm. So in what we call liquid slurry storage, that is also what IPCC for greenhouse gas inventories, that's the term they use. So it's not an anaerobic lagoon, just to clarify that. So the digestate is stored in the same way, so in that same system, and it's generally more common to not have a cover and flare over that, but you obviously could. And there's at least actually there's a few more farms now than there used to be, whatever. It's only been in the last 5 years or so that some have opted to put a cover and flare over their digestate storage. So we are kind of separately, we kind of have another effort to really analyze those systems to really quantify the gas production rate and the difference between digestate and manure. Um, so I guess, yeah, good question. One of the systems we analyzed here was digestate under a cover and flare. But, anyway, just so you know, one was in there at least. But
Mhm.
I think we need to still work on the data analysis that we do have from those meters on those systems to really understand digestate versus manure without
That, that
digesters.
that sounds awesome. But what you're saying is you have at least one system where you were measuring the amount of biogas that was going through the flare after a digester?
Yes.
Okay.
Yes. Yeah, we have more than we have many we have more of those. As far as in this study of just leak detection with mostly using that camera, we had one
Okay.
of the six. But yeah, we do have at least I think 4 or 5 that we're tracking now. But most of them are pretty new. So
hmm I mean, that
hoping to
sounds
have
like,
some more data on that and under another project.
yeah, that sounds like that'll
So
be really interesting data. And I think that's what a lot of us want to
yeah,
know is how much of that potential is really left.
right.
And then the last question that I have for you is when you sort of look at those digesters and the number of vents that seem to be
Mhm.
having methane coming out, was that sort of continuous overpressure event that always kept the vent working? Is it operating more like a leak? Do you have any feel for maybe what was causing those to almost always have gas coming out?
Yeah, good question. And I guess I'm thinking the fact that the digester systems, at least observed, um, I don't know, I think it was more vents than leaks, right?
hmm
I'm remembering that. And then sort of the question is why or what did we see? So and it was a variety. Actually, I guess what I should clarify on that, and I forgot to put this in the slides, or just it's important. We had at least two RNG systems, um, and I think that actually the rest were electricity. So
hmm
the reason I say that is because for RNG, and I'm not exactly sure which type of CO2 removal they used, but the ones that we looked at had a vent of that carbon dioxide, and there was trace amounts of methane, or what we would call fairly small methane, but we classified that as a vent because it's the
Hmm.
normal operation. And so what that means is some of the separation of the CO2 has some of the methane go with it. So I'm sorry, I should have mentioned that. But yeah, so that was one case. And with the electricity systems, I would say what we observed was there was some excess gas issues on a couple of them, and the flare was working, but I think they also had some periods where, or they had some issues with the pressure that was, um, alert, moving the gas to the flare versus to a pressure relief valve. So we did see pressure relief valves going when the flare was also going, and then also seeing when the flare was not working and the pressure relief valve was going. So some of these things needed to be really reanalyzed, or those types of balance of pressure issues, I think, is what I guess I would say. And yeah, so
Perfect. Thank you so much. I think that was a lot of great information. I do have one last question for you. And now that you've
mhm,
had quite a bit of experience with the FLIR camera, you
yes.
feel pretty comfortable detecting leaks. It seems to work relatively well. Any recommendations on what you like, didn't like about it, or you'd continue to use it in the future?
Yeah, we did use or have the GF77 model. I think that's still available, or it's the uncooled model. And it worked great. It's very robust in the field. It starts up very quickly, and we did use, I did show a picture of the camera looking at the cows, by the way. Looking for methane from cows is possible, and it's not that easy, but that was interesting to do a few
Mhm.
times. That's another, not my project, but anyway, you have to use a tripod, because if you don't, you don't have to, but unless it's like a big leak, you're not, it's going to be hard to really keep it steady and like, oh, I see something. I mean, I saw pinhole leaks. And then the interesting thing about like a pinhole in a cover. And the interesting thing about that is that it's very small, but like with covered manure storages, you don't have digested manure and you can smell odor easily. So if you are walking by, you could smell even a small leak. And I think so I guess part of what we're still working on is sifting through some of that information. Of course, we don't expect everybody to go out and buy a $30,000 camera or whatever they are now. I don't know. But what we do think is there's a lot of ways to actually know, or at least have some awareness of a leak, and then go and find it with maybe other tools like sniffers and things. But, be observant about odor. That definitely says there's a leak in a cover and flare, especially, and you've got to figure out where that is. So I guess there's just other ways. We saw bubbling in cases, right? That indicates gas coming through. If there's like water or some other liquid, I mean, we saw things like that. So kind of that's a big part of what we are hoping to sort through for more help, especially for, farmers or site operators that don't have a camera.
Mhm.
But yeah, we found it really, really useful as far as seeing exactly what was going on and
Per-
not going on. So.
Perfect. And then I do have to do a little bit of administration. So our next webinar is on June 9th at 1 p.m. And we have Dr. Tim Ellis here from Iowa State University in the Civil Engineering Department. And he's going to be talking with us about requirements for industrial and bioprocessing feedstocks and anaerobic digestion systems. I know he's done a bit of work here with some of the Iowa products. Uh, Up by Fort Dodge, so excited to hear about that. If you're interested in our anaerobic digestion newsletter, please stop by our website and get signed up. And then finally, if you or a friend you know would love to watch a past webinar, we keep an archive of past webinars on our YouTube channel. So that's at youtube.com and then slash at Dr. Manure. So feel free to stop by, recommend it to a friend, tell them that you can see great work with that FLIR camera, seeing leaks from covers and digesters, and how awesome the video really looked. So with that, thanks for joining us today, Lauren. Really appreciated the
Yeah.
presentation, and I love the great visuals of actually seeing the leaks and kind of what we probably should look at on digester systems to maybe do a little bit better job.
Yeah. Thank you, Dan. Thanks for the opportunity.